Hi, my name is Oktay. Welcome to today's video about the chemical element oxygen. This is a nice picture of the element oxygen, liquid oxygen. Its boiling point is minus 183 degrees Celsius, which is 90 Kelvin. Atomic number is 8. The name comes from the Greek oxygenes, which means acid forming. Oxygen was discovered in the 1770s by Carl Wilhelm Scheele and Joseph Priestley. And this discovery led to the end of the phlogiston theory, which was a theory about a fire-like element, phlogiston. This is a picture of the origin of the chemical elements of the nucleosynthesis. Oxygen is here, top right, as a member of the 6 main group of elements of the chalcogen group. And it is produced in exploding massive stars. The main isotope is the oxygen isotope 16 with 99.8%. And there are two more isotopes, oxygen 17 and 18. And there's a radioactive isotope, oxygen 15, with a half-life of 2 minutes. This is a picture of the nuclear fusion in an evolved massive star. This picture explains why oxygen 16 is the main isotope, because it's the direct product of the fusion of the second most abundant element in the universe, that's helium. 2 helium-4 isotopes merge to helium-8. 1 more helium, you get carbon-12, and 1 more helium is oxygen 16. This is a picture of the abundance of the chemical elements in Earth's crust. Oxygen is at number 1, most abundant, with about 49% of the Earth's crust. And in the universe, oxygen is number 3 in abundance, after hydrogen and helium. These are 3 examples of oxygen minerals. At the left, that's quartz, which is silicon dioxide from Tibet. In the middle, that's Brazilianite, which is sodium aluminum phosphate hydroxide from Brazil. And at the right, that's rosacite, which is copper, zinc, carbonate hydroxide from USA. This is what's special about the chemical element oxygen. That's it is number 2 in electronegativity. Electronegativity is the strength of an atom to attract electrons. You can see there's only one element that's higher, that's fluorine. Here are 3 examples of chemical reactions. At the top, that's the reaction of gold with oxygen. In air, gold does not react with oxygen, but you can make it react with addition of cyanide ions. Then you get this sodium dicyanoaurate complex. That's how you can isolate gold from ore. Second example is the reaction of xenon hexafluoride, which can be made from xenon and fluorine with water. That gives you the oxygen compound xenon trioxide plus hydrogen fluoride as byproduct. And at the bottom, that's the reaction of aluminium with oxygen. You get aluminium oxide. But in the case of aluminium, you get this effect called passivation. Once you have this thin layer of aluminium oxide, and that blocks the oxygen from the aluminium metal underneath. So this is like a layer of paint, and it stops further corrosion of the aluminium. You can check my aluminium video. I have explained this phenomenon in this video. This is a nice picture of the Earth's troposphere and from the ISS space station. Troposphere goes up to an altitude of about 12 kilometers. This is the composition of air by mole fraction. It's 78% nitrogen, 21% oxygen, 0.9% argon, 420 parts per million carbon dioxide, and then other noble gases, neon, helium, krypton, methane, and water vapor. This is a nice diagram. It shows you the development of the oxygen concentration in the air. throughout the Earth's history. So x-axis is time. We are now here. GA means gigayears, billion years. We are now at 21% oxygen. But you can see back a few billion years back, the oxygen concentration was very low. And in red and green, these are the estimations of the development of the concentration of oxygen. Photosynthesis was a big step in the evolution of life. It was invented 3.2 to 3.5 billion years ago. Life is at least 3.8 billion years old. That's this reaction, 6 carbon dioxide plus 6 water to glucose, C6H12O6 plus 6 oxygen as a byproduct. The invention of photosynthesis changed the reducing atmosphere into an oxidizing atmosphere. This is called the Great Oxidation Event, and it had many changes for the species as a consequence. This is a picture of how photosynthesis works. It is a multi-step redox reaction of water and carbon dioxide. There's the light reactions and the Calvin cycle. Important compounds are ATP, that's adenosine triphosphate, which is the energy molecule. And the energy is in the phosphate groups. And NADPH, that's the hydrogen transport molecule. These molecules make this reaction possible. Product is sugar, that's glucose. And excess glucose is converted to starch for storage. And the byproduct oxygen, that's where the 21% oxygen in the atmosphere comes from. This is a picture of the industrial oxygen production by fractional distillation of liquefied air. One big producer is company Linde. And this works because nitrogen has a boiling point of minus 196 degrees Celsius, and the heavier oxygen molecule has a higher boiling point of minus 183 degrees Celsius. These are industrial applications of oxygen. It is used for the steel production to remove sulfur and carbon. It is also used in the oil industry for sterilizing and purification of water. This is a nice animation of the human body. In the human body, the number one element by mass is oxygen. By number of atoms is hydrogen. 60% of the human body is water by weight. But proteins, fats, carbohydrates, and bones, all these compounds also contain oxygen. This is a transport molecule in the human body, that's hemoglobin. It is in the red blood cells. At the left, you can see the structure. It has a spiral structure part, and you can see here is a flat structure. The spiral structure is the protein globin, and this flat part is the Hem-B porphyrin ring. At the right, you can see the structure of this molecule. It's an aromatic compound. It's a central iron 2 ion, and the oxygen molecule is connected to the central iron 2 ion for transport. The radioactive isotope oxygen-15 has a half-life of 2 minutes. It can be produced in the cyclotron by hitting nitrogen isotopes with deuterons. Deuterons are the nuclear cores of the isotope deuterium. And you can use oxygen-15 in the positron emission tomography, for example, for brain imaging. And at the bottom, that's the decay reaction of oxygen-15. It decays to nitrogen-15 plus beta plus particle. Beta plus particle is the positron. Positron is the antiparticle of the electron. This is another allotrope of oxygen. Allotropes are different forms of the same chemical element. That's ozone O3. There's an angle of 116.8 degrees. This gentleman at the left, Christian Friedrich Schönbein, discovered ozone in 1839. O3 is a colorless gas with a sharp odor, and it is a strong oxidant. There's a simple test for ozone. That's the rubber band test. You can see at the top right, in the presence of ozone, the rubber band gets damaged. That's how you can detect ozone. This compound can be used for bleaching, pharmaceutical compounds, for disinfection, and in organic chemistry. This is how the ozone cycle works. This is an essential cycle for life on land. It was possible only after the invention of photosynthesis, which provided the oxygen for the atmosphere. The UV photons from the sun are absorbed by the oxygen molecules, and this splits them into oxygen atoms. They can react with other oxygen molecules, and you get O3. The O3 molecule can also absorb UV photons, and it decays back to oxygen. And this oxygen O2 and O3 cycle absorbs all the dangerous UV photons from the sun, so they can't no longer reach the Earth, and organic molecules that make up life are protected from these dangerous photons. This is a nice picture of the Palacio Real Aranjuez near Madrid in Spain. That's of water. Water is the life molecule. It is a solvent and reactant. I've made a separate video about the properties of water. It's the intermolecular hydrogen bond which gives the tiny molecule water the properties of a big molecule, like for example the big temperature range of liquid water from 0 to 100 degrees Celsius. Its density maximum at 4 degrees Celsius is high viscosity, high capacity for heat. Its dipole moment. And water is an ampholyte, which means one molecule can be an acid and another one can be a base. This is an interesting picture of a pillow basalt on the seafloor near Hawaii. This proves that water existed already 3.8 billion years ago, but there are other sources for water. One possibility is reflected planetesimals from 2.7 to 3.1 AU distance. 1 AU is Earth-Sun distance. They were deflected by the giant planet Jupiter. And this was only possible because Jupiter has a slightly eccentric orbit of 5%. That deflected these planetesimals into the inner solar system, and some of them crashed into Earth and brought the water. And there's another mechanism, that's the reaction of hydrogen with oxides in the dust disk in the early solar system. That's hydrogen. The hydrogen comes from the solar wind, from the sun, and the chemical reaction with the oxides in the dust disk produces water. And this disk lasted for many million years, so over time you get a significant amount of water with this mechanism to Earth. This is the annual mean sea surface concentration of dissolved oxygen. So pink color is a low concentration, and red and yellow, that's high concentration. And you can see in this picture, cold water can hold more dissolved oxygen than hot water or warm water. This is another hydrogen-oxygen compound, that's hydrogen peroxide, H2O2. It was discovered in 1818 by Louis-Jacques Sénard. He called it eau oxygénée, which means oxygenated water. And at the top, that's the chemical reaction for the anthraquinone process, which was invented by the German company BASF in 1939. That's the reduction of this compound anthraquinone with hydrogen, then you get anthra-hydroquinone. And the reaction with oxygen produces hydrogen peroxide, and you get back your catalyst anthraquinone. H2O2 can be used for pulp and paper bleaching, and for detergents, and in the organic chemistry. This is a nice animation of the annual variation in the biosphere from the years 2001 to 2017. The colors for the vegetation: brown means low concentration, dark green means lots of vegetation, and you can see the development of the phytoplankton. Purple is a low concentration and yellow is a high concentration. That's a very nice animation. It shows you the dynamic of life. That was today's video about the chemical element oxygen. Thank you for watching. Have a nice day. Bye bye.